5 reactor-powered systems keep Ford-class carriers launching and recovering jets without pause. Emails, catapults, advanced arresting gear, aircraft elevators, 11 weapons elevators, aviation fuel networks. The reality is, they're not 5 separate machines. They're one synchronized system that converts nuclear reactor output into non-stop flight deck tempo. Walk the deck during cyclic ops and you'll see it. An F/A-18 launches at 165 miles per hour. Another traps the wire behind you. Below deck, elevators move aircraft and ordnance, fuel pumps to refueling stations. Every cycle runs in tight loops. But here's what most people don't realize. These 5 systems were designed to do something Nimitz-class carriers can't match, and it changes everything about sustained sortie generation. Here are the 5 reactor-powered systems that keep carrier flight ops running non-stop. Launch, recovery, vertical movement, weapons flow, fuel delivery. Each one draws energy from the ship's nuclear plant and converts it into continuous deck tempo. On a Ford-class carrier, those systems are EMALS, AAG, aircraft elevators, weapons elevators, and the aviation fuel network. The reality is, they're not 5 separate gadgets. They're one synchronized machine built to turn reactor heat into air power without pause. Walk the flight deck during cyclic ops, and you'll see it. An FA-18 locks onto the catapult shuttle. EMALS fires. The jet vaults off the bow at 165 miles per hour in under 2 seconds. Behind you, another Super Hornet traps the 3-wire. AAG absorbs 44,000 pounds of kinetic energy in 340 feet of deck. Below deck, an aircraft elevator rises with an E-2D Hawkeye. Ordnance rides 11 electromagnetic weapons elevators from deep magazines to staging areas. JP-5 fuel pumps through miles of piping to deck edge stations for hot pit refueling. Every cycle, these 5 systems run in tight loops. Miss one beat, and the whole tempo suffers. Ford-class carriers re-architected that tempo by electrifying the bottlenecks. The A-1B reactors don't just boil water for steam turbines. They feed massive electrical generation capacity into a high-voltage distribution grid that powers launch, recovery, vertical logistics, weapons handling, and fuel movement. The truth is, Nimitz-class carriers do the same mission with steam catapults, hydraulic arresting gear, and older elevator designs. Ford took the systems that limit sortie generation and gave them electric power, precise control, and future capacity headroom. The goal wasn't flashy tech, it was throughput. How many aircraft you can launch, recover, move, arm, and refuel in a given window. The power flow is simple in concept. 2 A-1B reactors generate steam. Steam drives turbines. Turbines spin generators. Generators produce electricity at high voltage. That electricity feeds ship distribution buses. From those buses, power runs to EMALS energy storage, AAG motor generators, elevator drives, fuel pumps, cooling systems, landing aids, lighting, deck edge comms, and every other system that keeps the deck alive. What most people don't realize is that the A-1B plant was sized not just for today's flight ops, but for future systems the Navy hasn't even installed yet. Directed energy weapons, advanced sensors, next-generation aircraft with higher power demands. The electrical margin is already there, baked into the design, so adding those systems won't starve flight ops of the juice they need to maintain tempo. Why does this matter? Because in a peer fight, you don't win with one perfect cycle. You win by turning the deck again and again. Sustained sortie generation beats surge capability every time when the fight lasts days or weeks. Ford's 5 reactor-powered systems exist to deliver that sustained tempo. Launch becomes recovery. Recovery becomes movement. Movement becomes arming. Arming becomes fueling. Fueling becomes launch. The loop tightens. Delays shrink. Manning drops. Maintenance hours fall. And the reactors keep feeding power into the grid 24 hours a day, 365 days a year without refueling for decades. Ford-class carriers were built to raise sortie generation rates compared to Nimitz-class while reducing the crew size and maintenance burden. The 5 systems we're breaking down today are the hardware proof of that design philosophy. Each one closes a gap that used to slow the deck. Each one converts reactor output into mission tempo. And together, they form the reason Ford-class flight ops can run non-stop. System 1 is EMALS, the electromagnetic aircraft launch system. It replaces steam catapults with linear motors and does one job: convert ship power into precise launch energy for every aircraft. On Nimitz-class carriers, steam catapults use reactor steam to drive a piston that yanks the shuttle down the track. It works, but steam is hard to control. You get rough acceleration, high airframe stress, and narrow launch windows. EMALS fixes that by going electric. Here's the power flow. Ship generators feed. EMALS energy storage modules, capacitor banks, and flywheels that hold energy until launch. When the shooter triggers the CAT, stored energy dumps into linear motors under the deck. Those motors create a magnetic field that accelerates the shuttle smoothly. The system adjusts thrust in real time based on aircraft weight, wind, and sea state. An F-35C gets a different profile than an E-2D. A light load gets different energy than a max weight strike package. The result is smoother, more controllable launches across a much wider weight range than steam. Why does that matter for tempo? Smoother launches mean less airframe stress, longer service life, and fewer maintenance hours between sorties. Broader envelopes mean you can launch heavier future aircraft without redesigning the CAT. Electric power means no steam lines, accumulators, or massive hydraulics eating deck space and man-hours. By design, EMALS cuts launch crew size and maintenance versus steam. The truth is, it also gives the airboss flexibility to sequence launches without waiting for steam pressure to recover between shots. System 2 is AAG, Advanced Arresting Gear. It stops aircraft when they trap a wire. Nimitz class uses hydraulic cylinders to absorb energy by forcing fluid through valves. It's reliable but can't adjust on the fly, so every trap hits hard and wears fast. AAG replaces hydraulics with electric motors and a water twister energy absorber. When an aircraft catches the wire, motors pay out cable while the twister dissipates energy. The system monitors tension and speed in real time and adjusts braking to match weight and touchdown speed. The goal is tailored arrestments that reduce wear. Power flow is simple. Ship distribution feeds AAG motor controllers. Controllers drive the motors that manage cable payout. Sensors feed data so each arrestment fits the jet that just landed. A light FA-18 on a calm day gets a different stop than a heavy E-2D in rough seas. That precision stabilizes recovery cycles and cuts maintenance hours after every trap. When AAG works as intended, it tightens the recovery window and keeps aircraft flowing from wires to landing area to elevators without long pauses. Here's the candid part. Both EMALS and AAG hit reliability and certification problems early in the Ford program. EMALS had lower than expected mean cycles between failures. AAG took longer to certify across the full weight range. Those issues are documented in congressional reports and Navy updates. Fixes included hardware changes, software patches, and operational learning. The problems were real and slowed initial ops. But they weren't design flaws. They were first-of-class growing pains. Reliability growth that comes with any new system at sea. By mid-decade, both systems matured enough to support sustained cyclic ops. Follow-on Ford hulls incorporate fixes from CVN-78's experience, so reliability improves with each ship. The design intent remains. Electric launch and recovery aren't luxuries. They're tempo enablers. Smoother cycles, lower maintenance, broader envelopes, future headroom for heavier aircraft, and they free up space that steam and hydraulics used to consume. Launch and recovery electrified and stabilized, feeding the non-stop loop that starts and ends on the pointy end of the ship. Vertical logistics decides whether launch and recover becomes launch, recover, and turn. You can have the best catapults and arresting gear in the world, but if you can't move aircraft and ordnance fast between decks, your tempo dies. What most people don't realize is that the biggest bottleneck on a carrier isn't always the catapult, it's the lifts. Nimitz-class carriers have 4 aircraft elevators and 2 weapons elevators. Ford-class has 3 aircraft elevators and 11 weapons elevators. That trade looks strange until you understand the flow redesign behind it. System 3 is aircraft elevators. They move jets between the hangar bay and flight deck. Ford's 3 elevators are larger and have higher weight capacity than Nimitz's 4. The design trade was fewer platforms, bigger cycles, better positioning. Each Ford elevator can lift heavier loads and clear deck edges faster, reducing congestion during high-tempo ops. The elevators are powered by the ship's electrical plant, driving electric and hydraulic systems that raise and lower multi-ton aircraft safely under continuous pressure. Faster cycles mean aircraft spend less time waiting and more time in the launch or recovery sequence. A larger platform means you can move bigger aircraft or multiple smaller assets in one cycle. That cuts trips needed to shuffle the air wing between decks. Better deck edge placement means taxi conflicts drop. Aircraft flow from landing area to elevator to hangar without crossing active launch lanes or fouling recovery zones. The island relocation on Ford was part of this same flow redesign. Move the island, reposition the elevators, shrink taxi time, raise sortie generation rate. It's all connected. System 4 is where the real revelation lives. Weapons elevators. Ford has 11 electromagnetic weapons elevators compared to 2 on Nimitz class. Those 11 lifts move bombs, missiles, and ordnance from deep magazines up to assembly spaces and flight deck staging areas. They're electromagnetic, meaning linear motors powered by the ship's electrical grid replace the old wire rope and hydraulic systems. The result is faster movement, safer operation, and lower manning. But the bigger win is separation. Weapons flow and aircraft flow used to tangle on Nimitz. Ford splits those lanes by flooding the ship with dedicated weapons elevators. When you arm an aircraft on a Nimitz-class carrier, Ordnance rides a slower elevator, moves through shared passages, and competes for deck space with jets taxiing and recovering. Timing gets tight, delays stack. On Ford, weapons ride their own express lanes from magazine to staging. You can pre-position Ordnance near the flight deck while aircraft are still recovering or refueling. That tightens the arm-turn launch loop. The jet lands, traps, taxis, hits the elevator, drops to the hangar, gets inspected, rides back up, pulls forward to the arming area, and Ordnance is already waiting because it came up a separate shaft on a separate timeline. The loop accelerates. Like emails and AAG, the weapons elevators hit certification and reliability delays early in the Ford program. Some elevators took years longer than planned to reach full capability. Those delays are documented, but the architecture is sound. Follow-on ships benefit from lessons learned on CVN-78, and the tempo advantage remains. Separating weapons flow from aircraft flow removes a hidden choke point that used to throttle sortie generation even when cats and wires were running fine. System 5 is the one nobody sees until it stops. Aviation fuel, JP5, the lifeblood of flight ops. Ford-class carriers store thousands of gallons of jet fuel in tanks deep in the hull. That fuel must be filtered, temperature-controlled, pumped through miles of piping, and delivered to deck-edge stations at high flow rates so aircraft can refuel between sorties without killing tempo. Every pump, every valve, every filtration unit, every temperature sensor runs on electrical power from the ship's reactor-fed distribution grid. If the fuel stops moving clean and fast, the deck stops. Period. Here's the flow. JP5 sits in storage tanks below the waterline for safety and stability. Pumps pull fuel from storage and push it through filtration systems that strip out contaminants and water. Temperature control keeps the fuel within operating limits so it flows properly and doesn't cause engine problems. From filtration, fuel moves through a network of piping to flight deck refueling stations positioned at deck edges and in designated hot pit areas. During high-tempo ops, jets can land, trap, taxi to a hot pit station, take on fuel, and taxi back to the catapult without shutting down engines. That's sustained tempo, but it only works if fuel delivery is continuous, clean, and fast. The reality is, fueling happens in parallel with launch and recovery. While one jet is on the catapult and another is trapping a wire, a third might be taking on 8,000 pounds of JP5 at a deck edge station. The fuel system has to supply multiple stations simultaneously without pressure drops or flow interruptions. That demands serious pumping capacity, redundant piping, and tight monitoring. Reactor-powered electrical systems drive the pumps and run the control and monitoring networks that keep fuel moving under pressure 24 hours a day. Lose power to the fuel system and hot pit refueling stops. Turnaround time stretch. Sortie generation rate collapses. What most people don't realize is that fuel is the quiet, critical path. Emails and AAG get the attention because they're visible and dramatic. But if you can launch and recover all day but can't refuel aircraft fast enough to turn them, your sortie rate is still choked. The Ford-class aviation fuel system was designed for higher throughput to match the higher sortie generation targets the ship was built to hit. More flow capacity, more deck stations, better filtration, tighter integration with the electrical plant that powers the whole network. It's unglamorous, but it's essential. Now add the support systems that make Nonstop real. Landing aids like IFLOLS, JPALS, and ACLS guide recoveries in all weather and visibility. Jet blast deflectors cool with water. Fire main systems supply water for firefighting and washdown. Deck lighting, deck edge communications, compressed air, and crew spaces, all powered by the same reactor-fed grid. Each system supports flight ops tempo in ways that aren't obvious until one fails. A JBD that can't cool delays the next launch. A fire main that can't deliver pressure forces ops to pause. Deck lighting that flickers during night ops creates dangerous gaps in recovery cycles. This is the detail layer. 5 reactor-powered systems, emails, AAG, elevators, weapons elevators, aviation fuel, plus a web of support systems that enable them to run continuously under pressure. Together, they form the reason Ford-class carriers can sustain tempo that older designs can't match. match. The deck never sleeps because the reactors never stop feeding power into the grid that runs the entire machine. Here's what those 5 reactor-powered systems deliver by design: higher sortie generation potential, lower manning requirements, reduced maintenance burden, and electrical headroom for future systems the Navy hasn't installed yet. Ford-class carriers were built to launch and recover more aircraft per day than Nimitz-class, while doing it with fewer sailors and less downtime. That's not marketing. That's documented program intent backed by Congressional Research Service reporting and Navy planning documents. The 5 systems, EMALS, AAG, aircraft elevators, weapons elevators, and aviation fuel, exist to close the gaps that used to throttle tempo on older carriers. The outcomes are measurable. Design targets for Ford-class include sustained sortie rates around 160 aircraft per day and surge rates near 270. Nimitz-class baselines sit lower. The difference comes from electrification, deck flow redesign, and vertical logistics improvements. EMALS and AAG stabilize launch and recovery cycles with less maintenance than steam and hydraulics. Larger aircraft elevators and 11 weapons elevators cut movement delays and separate ordnance flow from aircraft flow. High-capacity fuel systems keep JP5 moving to deck stations without choking turnaround times. Every system was sized to support those higher sortie rates without burning out crews or breaking gear. Manning drops are real. Electromagnetic systems need fewer operators and maintainers than the steam, hydraulic, and wire rope systems they replaced. EMALS doesn't need steam plant technicians managing catapult accumulators. AAG doesn't need hydraulic specialists bleeding fluid and replacing seals after every dozen traps. Electromagnetic weapons elevators don't need teams inspecting wire rope for frays and replacing sheaves. The labor hours shift from corrective maintenance to monitoring and scheduled upkeep. Over a 50-year service life, that adds up to thousands of man-hours saved per system and hundreds of sailors the Navy doesn't have to recruit, train, and billet. Electrical margin is the hidden win. The A-1B reactors and the ship's high-voltage distribution grid were sized to power current flight ops and future systems at the same time. Directed energy weapons, high-power radars, advanced electronic warfare suites, next-generation aircraft with bigger electrical demands. The capacity is already there. Adding those systems won't force the Navy to choose between running EMALS or charging a laser. The reactors can do both. Here's the honest status. First-class ships always take time to reach full capability. CVN 78. Gerald R. Ford hit reliability and certification challenges with EMALS, AAG, and weapons elevators. Some systems took years longer than planned to mature. Those delays are documented and real, but the architecture works. Fixes from Ford's shakedown experience flow into follow-on ships. Each hull benefits from lessons learned. Reliability grows. Certification timelines compress. Why does all of this matter? Because in a real fight against a peer adversary, you don't win with a single perfect mission. You win by turning the deck again and again, day after day, until the other side can't match your tempo. Ford's 5 reactor-powered systems exist to deliver that sustained tempo under pressure. Launch becomes recovery. Recovery becomes movement. Movement becomes arming. Arming becomes fueling. Fueling becomes launch. The loop tightens. Delays shrink. And the reactors keep feeding power into the grid without pause. If you want more deep dives into the engineering and operations that keep the fleet ready, hit subscribe and turn on notifications. Type proud in the comments if you back the sailors and crews who keep this reactor-powered machine running at sea. They're out there right now, turning nuclear power into air power 24 hours a day, 365 days a year.